Welcome to lesson 3 in our series on gravitational phenomena and orbital motion. Here we are, lesson 3, orbital motion. So we are going to talk about, well, a satellite that orbits a planet. Now, a moon is a satellite, technically. We're going to make some assumptions soon that, account for some things we're not really prepared to deal with. So kind of hang on for that. But let's just take the case of a planet of mass m and a big M and a satellite of mass little m, and let's assume that this satellite moves in a circular orbit. All right. Well, in our previous lesson, we said, these two objects, what do they do? Well, what they do is they exert gravitational forces on each other. That here's a force on little m by big M. Here's a force on big M by little m. Those two forces are equal and opposite by definition. And in our last lesson, what we said is, hey, imagine we hold mass m there and release it, and it's allowed to free fall. And what's its acceleration? And we drew the same exact free body diagram, and we generated an expression for how fast this object will accelerate. Well, guess what? Even if this thing happens to be moving in a circular orbit, like we are assuming that it is now, well, that's still the only force acting on the object. So one of the big things is that orbit is free fall. Right? This thing that moves in a circle does so because of the one and only force acting on it, which is the gravitational force exerted by mass big M. And so this thing is constantly accelerating toward the center of big M. Right? And as you know from circular motion, that's the definition of what it means to move in a circle, is to constantly accelerate toward the center of a path, where we don't change speed, but what this thing does if it moves in a circle is change direction at a uniform constant rate. All right, so this thing just happens to be moving. How did it get moving with this, this velocity that's tangent to its path? That's a harder question. But it is. This thing happens to be, why am I doing that in blue, moving at some speed vt, but the only force acting on it, that velocity is not a force. Let's be sure we baseline there. The only force acting on it is that gravitational force exerted by big M. So this thing is in free fall. All right. It just happens to be moving perpendicular to that free fall acceleration all the time. That's a big point. All right. And we could write a net F for this object, and we can say that F G on little m by big M accounts for little m's, in this case, centripetal acceleration. And well, there's a couple of ways to handle this gravitational force, but I'm going to do it like this. That is the mass of little m in big M's field. Well, that equals little m's, the product of little m's mass and acceleration. Now, worth noting, right, these are two different ways of thinking and looking at, considering what mass is. Over here, right, this mass here is what we call gravitational mass, right? The fact that gravity does a couple of things, or excuse me, mass does a couple of things. Mass, by its nature, creates gravitational field and feels the effect of other gravitational fields. This over here has to do with the fact that objects resist acceleration. Right? This comes from Newton's second law that says A is net F over M, where M is a measure of inertia. So this is over here the gravitational side. This is the inertial side. This is quite literally what we call gravitational mass. This is what we call inertial mass. But due to any experiment that's ever been performed, those two are equivalent. And so what we see, just like we saw in our, take mass m here and release it, the acceleration of this object is g, regardless of the mass of the orbiter. All right. So whether this is an object that is held here and released, and that force creates an acceleration towards the center, or this thing happens to be moving tangent to this path and thus perpendicular to this acceleration, no matter what, the acceleration is g. In this case, it happens to be a centripetal acceleration. That's a c, not a g. So, that acceleration depends on, well, big M's field, capital M, r squared, where here's r from here to there. Okay? But a pretty neat point here. Anything that is orbiting is in free fall. Just happens to be moving. Okay, now, a little more detail. Let's actually write an expression for this object's orbital speed. Again, let's make a couple of assumptions, important ones. One, orbit is circular. Okay, and so here's how we're going to do it. We're going to say, well, here is the gravitational force on little m by big M. We might as well just state the fact that there is also a gravitational force exerted on big M by little m. Those two forces are a force pair and thus equal and opposite. And our net F says that, well, Fg exerted on little m by big M equals little m AC. Okay, now we are writing, this is a net F for mass M. That's why this is mass M, right? This is orbiter. Now, a minute ago, what we did last slide is we expressed our gravitational force in terms of object little m's mass and object big M's field. But what we can also do is we can write this gravitational field the way that Newton expressed, which is big G times the product of masses divided by r squared. And this is, well, that is again little m. And AC we can call V squared over r. Now, these r's, it can be very simple to say, oh, there are r's, algebraically r's are equivalent, and so we can multiply both sides by at least one factor of r. But let's just talk about what these r's mean. Okay, over here, this r means separation of centers. This r means radius of circular path. And those don't mean the same thing. They happen to be, if we're, quote, lucky, or if we make the right assumptions, then they are equivalent numerically, right? And we're going to call them equivalent numerically because we're going to say that little m is way smaller than big M. Because here's the deal. An Earth-Moon system, quite literally, where the difference in mass of the Earth and Moon is about 100 times, really 81 or so. All right. What doesn't necessarily happen is the Earth doesn't orbit around. Sorry, the Moon doesn't orbit around the Earth. It's not. I mean, we know that the Earth is also rotating or orbiting around the Sun. So it's not that certainly not that the Earth is just sitting there, but if we're even in the kind of frame of reference of the Earth, the Moon is not simply moving around the Earth. What does happen is the two objects, the Earth and Moon, both orbit around their common center of mass. All right, and so the folks at PhET here, as most of you are aware, PhET is a group of incredibly awesome simulations from the folks at University of Colorado at Boulder. So look at this. If we look at our Earth-Moon system, this is not to scale, folks, not to scale. But I want you to watch. This does show, quote, the real physics. It just doesn't happen to be drawn to scale. All right, and I want you to look at what's happening to the Earth here. The Earth is doing a little bit of wobbling. Yes. And so you can see when the moon is over here, the Earth is over here. When the moon shifts over here, the Earth shifts over here. And so there is a common location around which these two things actually orbit. And it's a location that's about, well, 81 times closer to Earth's center than it is to Moon's center, because that's where the Earth-Moon system's center of mass is. Okay? But look, if we do this, now we're on Earth satellite, well, you don't see any Earth wobble. And that's because a satellite, has a mass of maybe, I don't know, 1,000 kilograms. And the Earth has a mass of about 10 to the 24th kilograms. So 10 to the third versus 10 to the 24th, the Earth is 10 to the 21st times more massive than a satellite. So that means a Earth satellite system is 10 to the 21st times closer to Earth's center than it is to the satellite center. So for all intents and purposes, the center of mass of Earth, quote, satellite system, let's say it's not the moon, but quite literally like a man-made satellite, that center of mass is, for all intents and purposes, at the center of the Earth. All right? You follow me there? It's a subtle point, but an important one. So if the center of mass of the system, the satellite Earth system, is just about the same exact location as the Earth's center, then the Earth doesn't really move around that center of mass location because its center of mass is, the Earth's center of mass is at the center of mass of the Earth satellite system. And then separation of centers and circular path radius are the same distance. Okay? Whew. If that doesn't work for you, what you can do is just take that all with a grain of salt and say, all right, well, these R's really are the same thing. They're the same number. Again, they don't mean the same thing. That's why you'll never hear me say that gravitational force depends on radius. R here does not mean radius. It means this. It happens to be equal to radius of circular path as long as orbited object and orbiting object have super duper different masses. What is true is that this mass here, while it's a gravitational mass of the orbiter, and this mass here, that it's an inertial mass of the orbiter, are equivalent. So here's what we get. We get an expression for orbital speed. What's that? Well, it's actually this. And what does that depend on? Orbital speed depends on two things. It depends on the mass of, well, this one is the orbited, two T's? Orbiter. There you go, that's better. That's the orbited object. And of course, well, not of course, but it depends on, in this case, the separation between the two objects, which is the same thing as, which we can assume is the same thing if we make this assumption. We can assume that's the same as the orbital radius. Okay, so what that means is, this says, well, R, even though there's a square root, this still means that R is in the bottom of a fraction, and, well, V isn't. So there's an inverse square root relationship here, which basically says something like that. It says that as R gets smaller, V gets bigger. So the closer objects are, well, I mean, this generally is true for planetary orbits. Right? It is true that the closer objects are to Earth, the closer planets to Earth have orbital periods, they're years, that are smaller than Earth's. Mercury is whipping around the sun like that. And Venus is going like that, and Earth is going like this, and things go slower and slower and slower and slower as you get out farther and farther from the sun. Okay, it doesn't work Oops. It doesn't work exactly numerically the way our expression here for V does, because that assumes a circular orbit, and planetary orbits are really elliptical, yada, yada, yada. But this is how you generate for what we need to do, assuming that orbits are circular and that, well, the two kinds of R's are the same number. Well, this is orbital speed. You got to be able to get there. Okay? Fair enough? Okay, here's a question about Moon and Earth. And notice it says find its average linear speed. So that's going to allow us to say, even though these R's kind of vary from each other, we're going to assume they're the same thing. All right. But now we actually have a couple of, oh, I need the moon's mass. No, I don't. No, I don't. Let's find the relative speed of the moon relative to the center of Earth. So here's what we do. Guess what? Any problem that involves gravitational stuff, Fg on moon by Earth, start with a net F in the centripetal direction. Fg on moon by Earth equals m moon AC. This is G, mass of the moon, mass of the Earth, over separation of two objects squared. That equals mass of the moon times V, well, let's say V average over R. Now, again, these two R's don't mean the same thing, but since we're talking about on average, let's call these things equivalent. And mass of the moon is irrelevant. That's why it's not provided. And whoops, this is a squared, mv squared. Okay, so our V average is, oh boy, 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. There's G. Earth's mass, 5.98 times 10 to the 24th kilograms over R. Average distance 3.84 times 10 to the 8th meters. All right, so you get out your calculator, you bang this thing out. I'll do it once I pause. And you get that V average of the moon is about, whoops, that, 1,000 meters per second relative to Earth's center. I mean, it's a big number, I suppose. It's not that big. I don't know. Now, what does that mean about the moon's orbital period? Now, remember, this means, period means time for one revolution. In this case, path around the Earth. Well, this is an important derivation to be able to do also. This was actually, oh boy, this was asked on the AP exam, I believe in 2019, spring of 2019. So we want orbital period. Remember, the one place where we see orbital period is we can relate the speed of an object to the distance it travels in a known amount of time. 2 pi r is the distance around a full circular path, and capital T by definition is called the period. So distance in one circular path divided by time for one circular path. Okay, well, look what we can do. We have an expression for V. V comes from here. V is the square root of Gm over R. That's 2 pi r over t. Okay, the way that you'll see this done is like this. Let's square both sides because I say so. G m over r is 4 pi squared r squared over t squared. And I'm going to get the t stuff by itself. I'm going to cross multiply. T squared g m is 4 pi squared r cubed. Okay, so t squared is 4 pi squared over g m r cubed. I'd write it like that because that's a thing that has been important to scientists for the last, how many hundreds of years? That's called Kepler's third law. That's Johann Kepler came up with three super duper important, as they apply to planetary motion, three super important laws. One of them that sure helped a lot of scientists figure out what the heck seemed wrong with their data for hundreds of years before that was planetary orbits aren't circles. I mean, first it's not that everything's orbiting the Earth, but that wasn't Kepler, right? Actually, it's that planets are orbiting the sun. That was a revelation. And then Kepler says, hey, planetary orbits, if we consider them to be what are called ellipses and not circles, then suddenly a lot of data seems to fit a lot better. People are getting pretty darn good at using telescopes and collecting data with pretty high degrees of precision. And when Kepler applied the mathematics of the geometry of ellipses to this data, a lot of stuff worked out really well. That led Newton to have to develop calculus to talk about the fact that, well, GMM over R squared, that gravitational force, was not constant because R wasn't constant in an ellipse. And so that developed a whole enormous branch of, well, mathematics. But anyway, one of Kepler's laws is that planetary orbits are ellipses. A second of his laws, actually called the third law, is this one. And it says that orbital periods, look, this stuff, orbital periods are a bunch of stuff that's constant times the cube, well, the square of an orbital period of any planet depends really only on how far away it is from the thing that's being orbited. Which is what we said a minute ago. We said if this is the sun, right, and here's Mercury, Mercury's screaming around, and here's Venus, a little slower, a little longer period. Here's Mercury's Earth, a little slower, a little longer period. Here's Mars, a little slower, a longer period, right? That's what this says. That's what Kepler's third law says. It says quite literally that the square of orbital period is directly related, right, because this stuff is all a number, to the cube of semi-major axis. Okay, that means, for all intents and purposes, average radius. Okay, so we can do all this stuff for t. I mean, you really then do this. You do the square root of the 4 pi squared, over g m, and this would be m of the Earth, the orbited, right? That comes from over here, orbited, times r cubed. So you plug all those numbers. I'm not writing them. You can plug them all in, and you'll get a big number of seconds. Then you can convert that number of seconds to a number of minutes. You can convert that number of minutes to a number of hours. You can convert that number of hours to a number of days. And guess what you're going to get? You know how long it takes the moon to go around the Earth? About a month, but less. So when you pound these numbers out, you're going to get a number of days that it takes the moon to go around the Earth. And if you use the numbers here, you're going to end up with 27.4 days. See if you can get there. Again, you're going to start with some hundreds of thousands of seconds. But if you keep doing conversions, you'll come out to this number in days. So this Kepler's third law, I don't want this to seem like the conclusion of this lesson. I took some time to make sure we do it because AP asked this question and because Kepler's third law is fundamental to the way planetary orbits behave. But the more important thing, the real focus of this is supposed to be that we can derive an expression for the orbital speed of an object. All right, and we do so, luckily, by not employing any super duper new physics at all. For us, we say, well, we draw a free body diagram, we write a net-F statement, we expand on what we know things to be equivalent to, and then we, ideally make some, understand some assumptions. But if we don't understand those assumptions, okay, it's not the worst thing in the world to just say, yeah, R is R, okay. But boy, I felt a lot better once I got the got the once I got the true definition of, yeah, those R's don't really mean the same thing, but are they the same? Well, they are the same if we make some assumptions. I don't know. That's a little bit deeper knowledge. And then we can, we can quantify, or we can express at least, how fast things move when they're in orbit. One of the tricky things is to keep track of which thing is the orbiter and which thing is the orbited. All right, which mass goes away with which mass goes in which place. Well, that can really help, I think, in using some of this on-by notation. Okay. And then we can apply that stuff to a pretty complex situation here about orbital period. And here's a nice little challenger for you. Okay. Says a satellite in what's called geostationary Earth orbit is always over the exact same place on Earth. All right. So, a lot of satellites are whipping around pretty fast over Earth, and they might orbit in a number of minutes, but those things don't stay over the same location on Earth all the time. But there are other pretty high altitude orbits that do this. All right, so a satellite can be directly over the same exact place on Earth all the time, and that's a big hint for you later. So what you can try to do is, using what you know about this orbital period, you can find what's called the orbital altitude. And altitude means height above Earth's surface, which is a little bit different than, it's not an orbital radius, but you're going to have to first find orbital radius and then make a little bit of an adjustment. So you can do some pretty advanced stuff with what we know now about orbital motion, orbital speed, orbital period, those sorts of things. Okay? Okay, folks, so what I would truly try to focus on is this part. It looks simple. It's 1, 2, 3 lines of algebra, but there's a lot of good science and physics in there. Okay? Okay, fairly well.